Taste, taste. Yeah. All right, so we kind of talked about this when we talked about olfactory senses, your sense of smell, but 3/5 of taste is smell. Um, and like I said before, you can see that when you're trying to eat and you're sick and you have a very stuffy nose and your nasal passage is very blocked. You can't really taste that well. The other fifth is vision and texture, and then the last fifth is actually taste. So taste buds are your organs of taste. You have about 10,000 of them, and they're found on the surface of your tongue, the roof of your mouth, the linings of your cheek, and the walls of your pharynx. So they're all up in your mouth. Um, on each taste bud, there is 50 to 150 taste cells, also called gustatory cells, Gustatory, and those gustatory cells are what's functioning as our receptors. Um, so the taste cells are the neurons, and they have very specialized microvilli, and those microvilli have the receptor sites for chemicals to bind to them. The taste buds are very specific to certain tastes. There's salt, sour, bitter, sweet. Alkali is a classification under bitter, and there's also a new one called umami. Um, Also on the taste bud, there's also epithelial support cells, very similar to the olfactory cells. So here we look, if we take one taste bud, the papillae is what we call the protrusion of the taste bud, and if you've looked at your tongue really close, you've seen these circles. And then we take a cross section of that taste bud, and we can see here, so we have our taste cells, which are shown here in pink, and then they're interlaced with support cells, those epithelial support cells. There are tiny projections that are called microvilli, and those microvilli we call taste hairs. They're seen here. And those taste hairs protrude from what's called the taste pore, which is a pore created, it's just an opening where the cells, the microvilli, come out of. The hairs are the very sensitive part of the receptor cells. They're the ones that are binding to chemicals that you're eating. Here's another diagram just showing, so here we have our support cells and our taste cells. Here's our taste hairs coming out of our taste pore. Interwoven around all of the taste cells and within the taste cells is the sensory nerve fibers. Remember, fibers, we're just saying axons and dendrites. So the ends of the nerve fibers are very close to the receptor cells, so that when a chemical is bound to the receptor cell, it becomes depolarized and sends the impulse very quickly to the sensory nerve fibers and then further to the brain. So here, once the sensory impulse reaches the taste receptor, it will travel along that receptor to the cranial nerve, and then from the cranial nerve it'll go up through the medulla to the thalamus and then end its way at the gustatory cortex. And the gustatory cortex is what's responsible for our perceptions of taste. So that's how is our brain interpreting those taste sensations. And that is located in the frontal lobe, in the cerebral cortex, and it's also in the insula. And the insula is a deep fold in the lateral sulcus, and it's also part of the cerebral cortex. So very much with your olfactory senses where mucus played a large role, in taste, saliva or spit plays a very large role. So we have to dissolve the chemicals that you are ingesting for them to bind to the receptors on the microvilli of the taste cells. And also, just like with smell, it's a combination of chemicals binding, not just one chemical binding to one receptor to develop a taste. It's multiple chemicals, a whole combination, binding to many receptors, and that combination creates a taste. Once the receptors bind, you depolarize that taste cell, and that will send the impulse to the sensory neuron and then on to the brain. So there's different taste areas in your tongue. This is sort of a misconception because all taste cells respond to more than one taste sensation, but there is a predominant area for each taste, even though you do taste multiple tastes in these areas. But typically, the tip of your tongue is where you taste your sweet. The rim of your tongue in the front and the sides, so kind of the outer area of your tongue, is where you taste salt. The sides is sour, and then the back of your tongue is bitter. So you can kind of test yourself here with the ugliest looking tongue I've ever seen. So we would have our sweet here, our salty here, sour here, and our bitter here. Salty is also found just kind of throughout the tongue as it is such a strong taste. So we are extremely sensitive to bitter taste, and that is inherited. Some people are extremely sensitive to bitter taste, and we're going to test this. It is genetic. But in terms of sugar, we can detect 1 part in 200 parts water. For salt, we can determine 1 part in 400 parts. For the sour taste, which is typically acid, so you're detecting hydrogen ions, we can taste 1 part in 130,000. And then bitter, we can taste 1 part in 2 million. So we are, of all the tastes, more sensitive to bitter taste. And that is evolution, because typically bitter tastes are associated with poisons. So if we sense it better, we tend to spit it out, therefore not ingesting a poisonous material, which is a positive. Alkaloids, which I talked about earlier, they are a group of bitter compounds, and those are typically the very poisonous materials. So we spit those out to avoid ingesting that poison. I also mentioned umami. So umami is a taste that's been recognized in Japan for a very long time, and it's only recently been recognized in the US. It's hard to describe what umami is, but some people describe it as very savory, pungent, or a meaty taste. I've heard it as a taste that kind of overtakes your whole taste. It kind of really fills your mouth and takes over and gives you a really intense experience. And that's just me watching the Food Network too often. Other taste factors, there are pain receptors associated with taste. Hot peppers, capsaicin is the chemical, and that will trigger pain receptors. Also, cold receptors can make you feel a cool sensation, and heat receptors can make you feel a burning sensation. So babies have taste buds on the sides and the roofs of their mouths just like we do. So they are more sensitive to stronger tastes. If you watched babies eating lemons, it is hilarious, but they are more sensitive to those strong tastes than we are as adults. And our sensitivity to taste decreases as we age. So in adults, we prefer saltier and spicier foods than kids because they are so sensitive to those tastes. So taste receptors are super similar to olfactory receptors. They work in tangent most of the time, in that there's a rapid sensory adaptation, meaning we stop tasting a food if it stays in the same place in our mouth, unless the strength of the sensation changes. So what we do is we move food around our tongue, and that stimulates different receptors at different times because we're binding those chemicals to different receptors. Also, over time, your sense of taste is not likely to diminish with age, much like your sense of smell, because your taste cells are modified epithelial cells, so they still undergo mitosis. Your taste cells and your taste buds are replaced every 3 days, which is fast. So you have new taste buds every 3 days. So the PTC test is a test that shows if you inherited an extreme sensitivity to bitterness. And I have PTC paper, and when we do the taste lab, I'm going to give you each a piece of PTC paper, and all you do is put it on your tongue. And some of us will taste extreme bitterness, and some of us will taste nothing. And it seems crazy that people taste nothing because it does, to me, taste terrible. There is also a difference between hot and cold food, and it all goes back to moving food and chemicals moving around your tongue to bind to different receptors. So hot materials, the molecules, the atoms are moving faster. So hot foods tend to have a stronger taste because the molecules in the food are moving around. They're dissolving faster, they're binding to your taste cells faster, and they're binding to more taste cells faster. So if you've ever had cold pizza, which I love, and hot pizza. Next time you eat cold pizza or hot pizza, think of which one is spicier, which one is evoking more taste. So, what's the point of taste? So, sweetness of sugar, pleasantness of saltiness, of sodium and calcium drive our intake for these essential nutrients. So, these are nutrients that we need. We need to ingest sulfur, phosphorus, oxygen, nitrogen, carbon, and hydrogen. And to ingest those, most of them we need to eat. So there's an example of these two twins, young children. They're called the Beaver twins because they ate the wood of their crib because they were in such need of a mineral in the wood, and that drove them to eat their crib. Crazy, but they needed those minerals, and it drove that. It's also taste is also necessary for us to reject harmful foods. So, like I said before, bitter is usually an indication of toxins or poisons, and we don't want to ingest that. And sour is an indicator of spoiled food. We don't want to ingest that either. So, in sour foods, the amount of hydrogen ions is increased, causing a very acidic or sour taste. And we do that a lot. We smell our food before we eat it to see if it smells sour. If it smells sour, we don't eat it. Correct? All right. This was a shorter one than usual, and I will see you guys tomorrow, Wednesday. I'm in Minnesota right now. It's super cool, super legit, like cool, like cold, like very cold. My cab driver was really awesome and said that people from California smile a lot compared to people from Minnesota. So kudos to us Californians for smiling all the time. All right, guys, miss you, and I'll see you Wednesday.